Okay. Oh, wait, that's not right. It needs to be full. Wait, where'd it go? There we go. Okay. All right, everyone. So today we're going to be talking about types again. This time we're going to talk about how to make your own types. So thus far we've been using types provided to us by Swift. We've been using types that you would call primitive types in other languages. In Swift they aren't. They are all built in the same way that you're going to be building types, which is pretty cool. Which means we can also look at that code as example code if we're ever trying to do something similar. So to start with, we'll be looking at value types. After that, we're going to look at reference types, and then we're going to look at something called generics. This class and the next class have the most important foundational information regarding Swift that you're going to need for the later part of the class when we're actually building apps that interact with web services. Specifically, this is important for you to know for the next class, which is about protocols. That class is going to be probably the most important class for learning Swift as a language, because Swift is what Apple calls a protocol-oriented language, right? Most languages are some form of object-oriented nowadays, not all, but many. What I'm teaching today is kind of an object-oriented view of Swift, but it's missing most of the picture, okay? Most of the picture involves protocols, and that is the next class. It's a huge topic. I'm splitting it into 3 lectures in the best way I know how, but there's just so much. So I'm going to try and blitz through all of this. And then at the end, the generic section we're going to do as a workshop. So we're not going to be doing many slides. There will be a few, but primarily we're going to be coding. So, cool. Any questions before we move forward? Awesome. All right, so value types, enums, and structs. Let's talk about them. So to start with, what is a value type? A value type is what we've been working with thus far. Ints, doubles, strings, errors, right? Those are all value types. They use what's called assignment via copy, or assignment as copy, okay? So when you assign to a variable or a constant with a type that is a value type, what happens is you end up doing a copy. Now, that doesn't come into play here. It comes into play here. So first, the regular assignment, when you're creating a literal, it doesn't create that literal in memory and then copy it over to the pi's memory. That would be insane. It just creates it where pi's points, right? Now, here's the interesting thing. Old pi's, the variable, we are assigning it to be the same as the pi's variable, okay? So the pi's variable is an array of strings. It has a cherry, a peach, and an apple string, right? So we would expect that to be the same in old pi's, right? Now we're going to modify our pi list with a new type of pi, a beat pi, which just sounds delicious. So with a beat pi added to pi's, we can expect that when we print pi's, we see the full array, including beat pi's. What happens when we print old pi's? We don't see the beat. That's because when we assigned pi's to old pi's, it copied it. It created a duplicate of that array somewhere else in memory, and it was basically created new. That is the key thing to know about how value types work, is whenever you assign one to another, if you ever pass one into a function as a parameter, it will create a copy. It will duplicate the memory, okay? So if your value type is massive, talking like, I don't know, 500 megs or something like that, then whenever you pass it to another function, you're duplicating it. You're making another 500 megs, right? So value types, you want to keep them small, you want to keep them concise, you want to keep them tight, okay? Things like strings, things like arrays, things like integers, right? Yeah, okay, cool. So that's assignment as copy. So we're going to talk about two different kinds of value types right now. We're going to talk about enums and structs. First, we're going to look at enums. These are going to look familiar to you because we've already kind of seen them. So you'll recall this is how we create errors for error handling. It's very similar. We don't have the error kind of keyword added on at the end with the little, colon. Don't worry too much about that. That's going to be covered in class 4 when we talk about protocols, because that is an error protocol that you are assigning to the enum. But for now, we're just going to look at this enum. This is a basic enum. It covers the seasons, right? We have different cases, okay? An enum is basically a way of saying, hey, any variable or constant that I declare as this enum, as season, it's going to store a value, right? And that value is basically, on the back end, it's a number. So it's like the spring case is 0, and summer is 1, and fall is 2, and so on and so forth, right? So it's basically just kind of, a way to delineate between different cases, right? So a variable that is one or the other, right? It's one of these things, basically. So if you have a variable that is a season, it is a spring, summer, fall, or winter value, and that's what's in it. So the cool thing in Swift with enums that's a little different from other languages is because it's very good at inferring your type, Swift can allow you to do a little shortcut where instead of, for the most part, most of the time when you use an enum, instead of having to type the full enum where you're like season.fall, right? Because it knows that this is an array of seasons and it could only ever be a season in there, you can just do .fall and it'll figure it out. It knows, oh, that's season.fall, right? So we've got our cold seasons array, we have our warm seasons set, right? Creating enums with a bunch of different cases and sets of those enums is a big pattern for creating configurations in Swift. So if you want to be able to say like, oh, I want to, I have these like, a bunch of, networking configurations for my app, right? I want to be able to use IPv6 and use HTTPS and all this other stuff, right? You can add a bunch of your like different cases, right, of like capabilities that your app may or may not have at any given time based on what the user selects. And then you can maintain a set of those capabilities and just kind of add to or remove from that set as you go. And then you get pretty fast, instant sort of runtime checks to see, oh, is that configuration set? And it's also very easy to read at a code level, which is nice. Okay, so enums have a bunch of things that make them nice and easy to use, and also some things that make them complicated to use. So let's say you have a long enum, it's got tons of cases in it. Let's say we're looking at months in a year. That's 12 cases. In a file, that's going to be pretty long. It's going to take up a good portion of the screen, especially if you're really zoomed in, right? So you can just do this. Basically, if you just separate your cases with commas after the case keyword, it treats those as brand new cases. This is syntactically exactly the same as saying case March, case April, case May, and so on and so forth, right? One thing to note in Swift, the convention for enum cases is lowercase for the case, for the very first letter. In a lot of languages, they prefer uppercase for both the enum type and the enum case. In Swift, this is the convention. We prefer the lowercase for the actual case and then uppercase for the type definition. So next, we're going to talk about nested enums. Nested enums are a way to it is a subset of the concept of nested types, which is very similar to nested functions, which we talked about very briefly, I believe, last time, which is, when you create an enum, you are defining a scope, right? That's that block, of squiggly bracket, open, squiggly bracket, end, right? Within that block, there's only a certain set of things you can do. There are rules that Swift says, these are the things that are allowed. One of the things you can do is declare another enum, right? So when you do that, you're basically kind of locking that enum inside your other enum. So if you want to access it from outside, you need to call the outer enum and then the inner enum, and then that's its type, right? So this is what that looks like in practice, okay? So if we wanted to, delineate our year into seasons by month, right? We could do this thing where we create this nested season enum, and then we have our different season enums within it, and then the case covers the month for each nested enum. And then the way that we access that is by saying nested season dot spring dot March or April or May or so on and so forth, right? So basically you can just kind of continue to nest sort of forever and ever and ever. Not necessarily the best idea, but it's something you can do. So the really cool thing about enums in Swift, and the thing that also makes them kind of complicated, are associated values. So in Swift, every time you use an enum case, all you're getting is information about which case it is, essentially, right? Oh, this is a May object. It's May, right? That's the season, it's May, right? But sometimes you want some extra information added in as well, and that can be kind of dicey. It can be kind of hard to do. You might create your own other type that wraps around it, and then you're this type has a variable that is my enum, and then based on what that enum is, I'll store some data and so on and so forth. Enums in Swift let you do this anyway by default. So they have something called associated values. When you create your case, you can give it essentially a parameter list. This behaves very similarly to, but not exactly the same syntactically to, function definitions, okay? So if you wanted to, you can do this without providing an argument label or a parameter name at all. You can just put string inside the parentheses if you want. That is not what I would call best practice, but it is definitely something you can do. So now what happens is every time we create a animal.pet instance, right? Every time we instantiate, essentially, an animal.pet enum case, it also says, oh, hey, you said that I have a string associated with me, right? So make sure to define the string, right? If you don't pass it a string, you'll get a compiler error. It's required, right? So basically this is a way of kind of, baking that within. And then moving forward, you can access the name on the myPet variable by just doing myPet.name, because it's known that myPet is a animal type. You can't access it by myPet.name. There's a way to basically unwrap it, and I realize I don't think I have a slide for that, so I will show that when we workshop generics later if someone reminds me. Okay. So if you nest enums and use associated values and have those associated values be your nested enum types, you can do nonsense like this, where you basically say, okay, cool, so I have an upper enum art, right? And then within it, I have two cases, painting and sculpture. A painting always has a name and a painter associated with it, and that's all we really care about. But a sculpture has a name, a sculptor, and a material. And I want that material to also be defined by a material type, but I'd like that material type to be scoped just to sculpture, and I'd like that sculpture type to be scoped just to art, so that if I'm using sculptures or materials elsewhere in code, I don't accidentally run into this exact enum that I created, right? If I want to have a different kind of material enum, right? Like if I was doing, in addition to this, right, I had an enum for, 3D objects, right? And it's got a mesh and a material and so on and so forth, right? you'd want to use the same name, but you wouldn't be able to because you'd get a type collision where the types would have the same name and it would give you a compiler error and say, hey, you tried to create two things that are exactly the same, please pick one, right? So here, because you're scoping it within the other enums, you're basically creating what's called a namespace, which is just a fancy way of saying a longer type. So the type of material in this case is art.sculpture.material, not material. Unless you're within sculpture, in which case then it's just material, but that's a shorthand. You can still write art.sculpture.material if you want. Cool. Okay. So that's a lot about how to make enums. How do we use enums? What's their purpose? What's the advantage to them, right? Primarily, enums are used in switch statements. This isn't always true, but they are one of the reasons why switch statements exist, why they're so good, right? And in Swift, you get a lot of extra support from the compiler that helps you make sure that your switch statements are fully complete and capturing everything that could possibly happen, okay? So let's take a quick look. We have an enum here that we call profession. We've got lawyers, doctors, engineers, and comptrollers, right? So we create our profession constant. We set it to be doctor, and then, that's just kind of, so this will compile. That could be being passed into a function or from some other part of your code, and you're not really sure what it's going to be. And so then you can do a switch. And within that switch, you switch on the constant or variable, right, that has the type of enum, right? And you do things like case.lawyer, right? Once again, you get a shortcut here. Swift knows, okay, the profession constant has a type of profession enum on it, which means all the case options are just the different cases of the enum, right? It even uses the same keyword, case, right? And so that's there for you. So based on which case you are, you execute that block of code, as we've talked about with switches. One of the things that you'll run into with this too is that because switches require you to kind of cover all of the cases, before we were doing switches on like strings and ints and stuff, and it would be like, you haven't covered every single string that could exist. And we're like, yeah, we know there are an infinite number of strings that could exist, right? So we're not going to cover all of them. You can create a default case to cover that, right? Here, because you are fully exhausting all potential options from the switch, it does not require you to have a default case. It does encourage it with a warning, though, because if someone changes your enum, if someone adds a new profession for whatever reason later on, that will cause a compiler error here because you are now missing one of the cases and you're not enumerating it correctly. Okay, that's enums. So now we're going to talk about structs. Structs are a little more complicated, and a lot of what we're talking about with structs is also going to apply to classes. So before we talk about structs, any questions about enums? Yeah. Oh, so far so good. Okay, yeah, cool. All right, so structs. So a struct is a value type, just as an enum is, which means anytime it gets used, it gets copied, right? Or not used, sorry. Anytime you assign it or pass it, it gets copied, right? Structs are what most of your basic types are made of. So int, double, array, those are primarily made using structs, okay? Structs are your kind of bread and butter. If you're ever creating something that's kind of like a fundamental data type that you want to be using a lot in your code, you'll probably build it with a struct, okay? So this is how you define a struct at a very basic level. This is an empty struct. It doesn't do or hold anything in it right now, right? But this is syntactically, technically correct code, so we're doing the bare minimum here just to look at it. This struct, we're calling it vector3. It's going to be a vector that holds an x, y, and z value. That's the plan. When you are trying to instantiate a struct, that is to say, create an instance of it, okay? you call the name of the struct and then 2 parentheses, right? In Java, you would see this, it would be very similar, except there would be a new keyword in front of it, right? Or in C++, similar, right? Swift is like, yeah, we know what you're trying to do. You don't need a new keyword, okay, right? There's no other situation where you're going to call vector3 with the parentheses, right? So, once again, Swift tries to make your life a little easier. Also, this constant now knows what type it should be. It should be a vector3, okay? So this is also how you create classes, right? Same thing. And what's happening when you do this, just to cover it a little bit at a theory level, is every single struct and class has an initializer, which is a special function that you can call to create an instance. And creating an instance is what we went over in class 1 when we talked about types, where we talked about the compiler telling active memory, right, or your program telling active memory, hey, I need this much memory, and this is what's going to be stored in it. These are all the things that are going to be stored throughout that piece of memory that you're giving me, right? So the initializer is the thing that actually does that. In your initializer, that's where you kind of are going to make sure that all of the values and constants for your struct or class are set. So, and the way you call it is by doing this. Now, by default, structs give you one, but I think I have a slide about that, so we'll get to it. So here's our struct. It has stored properties now, so we have our x, y, and z that we talked about. They are all doubles, because when you're dealing with a 3D coordinate system, typically you want them to be some sort of floating point number rather than an integer. And then, so we have those 3 stored properties, right? So they are properties that just store something. A stored property is essentially just like a variable or a constant, same as we've talked about before. You declare them with var or let, same as we've done before. The only difference is that these variables and constants are tied to the instance of the type that you're creating. So in this case, we have a vector3, and every instance of vector3 has an x, a y, and a z, right? And so whenever you're using them, you can access those using dot syntax, and we'll look at that in a moment. So the other thing was that caused an error because structs, by default, create a default initializer. So you don't have to see an init function inside of the struct in order to know, oh, cool, okay, this struct has an initializer. And it is required in order to create a new instance to allocate the memory for and store the data for that struct type. And so here it basically said, oh, we're missing the arguments for x, y, and z. You're trying to call the initializer. I can see you're trying to call the initializer, but you're not giving me the information I need. This struct needs 3 doubles in order to exist, right? So in order to make that go away, you give it 3 doubles, okay? So in this case, then after that, you can access any of the information stored within that constant or variable that is of that structure class's type by using dot syntax. So essentially, from your constant or variable, you have vector, right? You say vector dot, and autocomplete will pull up a nice fancy list of all the things that you could possibly say, right? And at the top of the list are the things that you defined, right? You'll inherit a bunch of stuff just from the compiler, right? And depending on what you're doing, like there's going to be a bunch of noise in there, but the things you defined should be near the very top. So in this case, you'd see some autocomplete for X, Y, and Z, right? And that's because you're basically saying, oh, I want to access, on this instance of memory, the part of it that has this stored variable, I want to pull that out and look at it as if it was a variable or constant. So here we have our instance. We're creating it vector3 with the initializer. We're passing it 0, 1, and 1. And then in the print statement, we're accessing the x and the y, which we have set, and those are 0 and 1. So this print statement prints x, 0 and y 1. So it's a lame example of why instances and types are helpful, but we'll get to that. Okay. So this looks like a function. It smells like a function. It says func in front of it. It's not technically a function. It's what's called a method, right? But you can think of it as a function because in every other way it is basically exactly the same as a function. You define it in exactly the same way. It behaves in exactly the same way. You pass it parameters and it has a return type. All of those things, same as functions. The only difference is that it acts within the scope of whatever type you define it on, and then you can access it. You can call that function using dot syntax, just like we were using to access the stored properties. So in this case, we want to calculate the magnitude of this vector. The magnitude of a vector, if you recall your basic, linear algebra, if you ever took it, or some other class. Geometry? Does geometry cover that? I don't remember. Anyway, it's the square root of all of the elements of the vector squared added up, right? So the sum of the square of each element of the vector, right? So in this case, we are saying, oh, cool. So we have a method named magnitude on vector 3. That means every single instance of a vector 3 has the ability to call the magnitude function. And then within the magnitude function, we have access to that particular instance's stored properties x, y, and z, right? And so whenever we do that, we can, we have our vector instance. And now when we call vector.magnitude, in order to calculate the magnitude, it uses the stored properties x, y, and z that we have already set by calling the initializer, right? And so therefore, what we print for distance is 1.4142 blah, 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 right? Which is like a, it's like a unit vector for, or it's not a unit vector, whatever. You recognize that number if you mess with vectors a lot because it's like the 1.0 in either direction. It's the diagonal between those. So, cool. Okay. So, there's also something called computed properties. They're different from stored properties in that computed properties don't actually store any data in memory. They run code whenever you call them, okay? They're kind of like functions. They're just a fancier, different way of doing the same thing that functions do, right? They're not exactly the same as functions because you can't pass them parameters, but they're essentially a parameterless function with one return type, right? So computed properties in Swift have two kind of sub pieces to them that you can use, right? One is called get, right? Where you basically, can using stored properties and other information on that particular instance, you can return some piece of information. In this case, we are just going to calculate the magnitude, right? But then we can also have something called set. And we define basically in those parentheses next to set, that is the name of the constant that is being set to that property, to that computed property. So if you were to say, vector dot magnitude equals 1, right? Then what's going to happen is your code's going to come in here. It's going to go, oh, okay, cool. So we're setting magnitude. So we're going to go here. We're going to hit set. Then we're going to pass in 1, right? So 1 is the value stored in new magnitude, right? Now, if you set the magnitude to 1 in this case, right, it's gonna just multiply everything by 1, which means nothing changes, right? But if you set magnitude to 2 or whatever, that would multiply. Yeah, what's up? So new magnitude, and I realize I don't have a good example shown here in the slide. So let me see if I can pull this up because that is a great question. The question was basically is magnitude or is new magnitude the right is an object of magnitude or just a new property name? Right. And as in to say, was new magnitude automatically calculated, like by Swift? Can I set it to whatever I want? Is that kind of what you're asking? Okay, so yeah, you're basically defining a parameter for the set function that gets used whenever you assign to that computed property. So let me get this pulled up here because I think that could help. And this is in the structs. So where are we? Calculated properties. Cool. Okay. And I have it defined somewhere else, so I need to comment that out. Okay. So if I bring this over here and minimize that, and then my mouse is everywhere. Okay, one sec. Bear with. Here we go. Okay, so here's that code. Oh, let me blow it up a bit. All right, so here we're doing the same thing as before with the distance, right? But let's say we wanted to set the magnitude, right? By the way, this is also not what happens. Like if you this is not mathematically correct with vectors, so don't worry about that. It was just an example, right? So we've got vector, right? This is our vector3 type, right? So you get autocomplete here, which is nice. So then you do dot and magnitudes here. It's an option. It looks like a property. It has this little P symbol. That means it's a property. It doesn't hugely matter to us if it is a stored or computed property because this computed property has a getter and a setter, which means to everyone outside of the instance, of the type, it's basically the same thing as a stored property. Okay, we don't care about the implementation details of what it's doing on the inside, right? So if we set magnitude here to 10, right? Because this is a let, right? Then we will essentially see a very different print. So let me see if this will print. It should be something like that multiplied by 10. Yeah, 14.142, blah, 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 right? So it multiplied everything by 10, which means magnitude, when you calculate it, now is something different, right? Because in here, then we're modifying our stored properties using this times equals, which is syntactically exactly the same as this, right? We're assigning, x times new magnitude to x, okay? Yeah, what's up?
The new magnitude, is it what you get from the get function, or is it 10?
So the question was, is the new magnitude what you get from the get function or what you put? And so the new magnitude here, this is just a name that we provide, so we could say new value as another one, right? It's custom, it's basically a property, and its type must be the same type as magnitude, right? And this set kind of definition is basically saying, hey, if anyone ever uses the assignment operator for this particular property, then call this function essentially with this parameter using the value that you assigned. So this ends up being syntactically the same as this, right? Now this is not technically syntactically correct, right? But yeah, does that answer the question?
So get would be vector.magnitude, and that would trigger the get function.
Yeah, so if you're ever using this, basically get is what gets called whenever you do vector.magnitude, unless vector.magnitude is on the left-hand side of an assignment operator, right? Unless you're assigning to it. If you're ever trying to set something to it, if you're ever trying to set anything into there, if you're trying to store any value inside of that property, as you would with, say, vector I can't type. There we go. Dot x equals 2, right? It's the same thing, right? So vector.x equals 2, right? That stores 2 into the x variable, x property on the vector3 instance. Does that answer the question? Cool. All right. Did anyone else have any other questions about the computed properties? Because I know this is not super intuitive. So, okay, cool. We're all good. All righty. Back to it. Okay, so those are computed properties. there's also, I think there's like a shortcut too, where you can have read-only computed properties. If you do not define a setter, then anytime you try to set a value to that property, you'll get a compiler error. It's a read-only property, so you can only pull from it, right? You can only read it. So, and that's if you do not provide a set block inside of your computed property. Okay. So, oh, cool. Yeah. Whoa, slow down, my friend. Here we go. Okay. I had some automated stuff going there, apparently. So in this case, this is the same thing as having that get wrapper with a return statement around the square root thing. Swift just allows you to say, if it's a read-only computed property, it's like, oh, that's a bunch of extra like boilerplate that you don't need. So you can just do it like this, right? We will assume if there is a single expression inside of your block, then that is what's being returned. That's the same thing that we've seen with closures, same thing we've seen with functions, right? Anytime you have a block, if it has a single expression in it, and that block is expected to return something, Swift will just say, okay, cool, you don't need the return keyword, we know what you're doing. All right, so there's also something called lazy stored properties, okay? So lazy stored properties are basically the same as your regular property. The main difference is that your regular stored property, the main difference is that they don't get set until you first try and read them, okay? So if you're first ever calling, magnitude, right? Normally, when you instantiate your struct, if you've set a default value for a property, like 1 or 0 or something like that, it gets assigned as soon as you instantiate that property. So as soon as you call vector3 parentheses blah, 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 if you have any property with an equal sign where you do an assignment of a value into it, then that's a default value for that property. And that happens when you initialize your instance. When it's a lazy property, it does not assign the expression or value on the right-hand side of the assignment operator to your stored lazy property until you try to access it the first time. So instead of it happening at initialization, it just waits. This is helpful for things that are computationally expensive, things like calling a service or running through like thousands and thousands of items in an array to build something really big. And you want to be able to create a bunch of create an instance without it locking up and slowing down your program, and you just want to do that later, right? So that's what a lazy property is. Okay. So I mentioned before, structs had a default initializer that gets automatically defined based on what properties you have, right? You can also create your own initializer, a custom initializer. In this case, we have created our own fancy initializer. There's a bunch of things in here that you might not have seen before. There is the self keyword. The self keyword is very similar to the this keyword in other languages. It's a way of saying, while you're within any given block of code that is running on your type, it's a way of accessing the particular instance that is calling that code, right? So when we do vector3 open parentheses blah, 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 and call this initializer, right, the memory got allocated, and now we're making sure it's filled with stuff, right? And the reason we have to make sure it's filled with stuff is because Swift requires all types to be non-optional unless you specify them as optional. So if we have a we have a property that's set to optional, you are not required to have it set in order for your initializer to complete. However, here, if we were to say not set magnitude here, when we call this initializer, we'd get a compiler error because magnitude doesn't have a value. And because magnitude doesn't have a value, that means it's nil. And we're not allowed to be nil. And Swift guarantees this at the compiler level when you call the initializer. And I just realized this is not full screen. It's like kind of full screen, but it's not full screen. Sorry. I am depriving you of pixels. Here we go. So you'd get a compiler error. Luckily, though, we can calculate the magnitude from the x, y, and z, right? So we just do that here, okay? We could also have magnitude be a parameter that we pass into the initializer. That doesn't really make any sense. That's not super helpful for our vector. Likewise, this also doesn't make a lot of sense, because if we ever were to modify the vector, then the magnitude would change, presumably, and we wouldn't be recalculating it, right? However, you'll note that this vector, these stored properties are all set to be constants, right? So they are constant stored properties, which means they can't be changed, right? So this vector is completely immutable. It cannot be ever modified, right? Which actually means that the magnitude will always be correct, right? So, yeah. Any questions about accessing your own properties using self dot? Yeah.
Is there a reason why magnitude doesn't get self dot in front of it?
Yes. So when you're accessing, great question. So the question was, sorry, I realized the micro. The question was, is there a reason that magnitude does not need to have the self dot keyword in front of it? And the answer is yes, there's a very good reason. And the good reason is that generally speaking, you don't want to use self dot if you can avoid it. Just because it's ugly, it's slow, not slow, it's harder to read, right? You'd prefer to use your properties as they are, as if they were just a variable that's within scope for you, right? However, we can't do that here because someone, aka me, because I wrote the function, right, named my parameters x, y, and z, the exact same things as the properties, as the stored properties x, y, and z, okay? So within this scope, you end up with this thing that Swift does, which is if you end up with multiple variables or constants that have the same name, the same identifier, Swift will pick whichever one is closest in scope, right? Whichever one was defined either in that scope or in the closest scope to it. Any higher up scope won't worry about it too much. Now, there's also instances where Swift will say, hey, you're trying to redefine something that already exists. What are you doing, right? I'm not going to enumerate all of those. The compiler will tell you when that happens. But when it doesn't happen, then you have to kind of watch out for stuff like this, right? So here, if you were to just say, you know, x equals x, right? If you as if you were trying to use the stored property x on the left-hand side and then the passed-in parameter x on the right-hand side, you'd get a compiler error because it would be trying to use the passed-in parameter x for both sides. It would try to assign it to itself, but as we recall from our functions talk, passed-in parameters are constants. They are let constants, which means they can't be changed, so you can't assign to them. So it would give you an error. So we use self dot to indicate, oh, these are the stored properties that have the same name as the parameters that were passed in. So we don't need it for magnitude because we didn't pass in a magnitude parameter to our initializer. That's the short answer, and then before that was the long, involved answer. So does that answer your question? Perfect. Okay. Any other questions about custom initializers and self? Cool. Okay. So now we're going to look at mutating functions. So by default, oh, sorry, one other thing about custom init. Well, pretty much everything we're talking about so far has been true for both structs and classes. We're going to talk about classes later today and get into them and a little bit what's different about them. But for the most part, all this stuff about properties and stored properties and initializers and everything and self, all that, the same between structs and classes, okay? This is kind of our first big difference, right? Which is mutating functions. So in Swift, structs are considered to be immutable by default. They do not want to allow you as a programmer to change them after you made them. This is a form of optimization. It allows structs to be very lightweight, stored in contiguous memory, that sort of thing, right? So it has this strong preference to be set to one thing and then stay that one thing forever without changing, right? However, because you can assign a struct to a variable and not only a constant, you could potentially, call some function, some method on said instance, right? And in that method, you might, change one of your properties, one of your stored properties, like we've done here, right? So we have this multiply by scalar double function that is a method on our vector3 struct, and we call it further down here by saying vector.multiply by 2. We're passing in 2, and yeah. Interestingly enough, if this error wasn't here, that would give an error too, because that's because 2 is an int, it doesn't have a dot, right? So I have a type error in my own code. Apologies, but that should be 2.0. So when you're within here, if you modify any of your stored properties, right, any of your instance's state, right? If you try to change any of the values that are stored within memory inside of the block of memory that is this particular instance of your type, then it mutates it, right? And the compiler will tell you, if you try to mutate a struct, hey, maybe don't do this, right? Here's a compiler error telling you, oh, this isn't immutable, right? It says self is immutable, right? And it's saying self is immutable even though we're not using the keyword self, because technically, behind the scenes, Swift is turning that line into self.x times equals scalar, right? It's the same thing, syntactically, okay? So basically, self is immutable. It doesn't want to change. It wants to stay the same. You get this compiler error. You really want your struct to be mutating. You really want to be able to multiply it. You want to be able to change its values as you go, right? In that case, then what you would do is modify your function with the mutating keyword. And that makes the error go away. You just tell it, yeah, I'm cool with that. My struct mutates, store it in memory differently. I'm not going to be as efficient. I don't care. I want to be able to change. And the compiler does it. It says, okay, your call, right? It's not a bad thing to make a mutating function on a struct, but if you're making a lot of mutating functions on structs, maybe consider a class instead. And we'll talk about why when we talk about classes. Okay, so next up we have statics. So the static keyword is a keyword that you'll see in a bunch of places, and basically what that keyword means is, hey, whatever I'm defining on this line, this static line, be it a method, be it a property, be it a computed property, whatever. You can make most of the things that we've made so far static. There's only ever going to be one of it, ever. And that exists for my entire type, right? So thus far, everything we've done has been instanced, right? So whenever you create a new type, a new instance of your type, right, it creates a block of memory for that. It stores all of the properties, and that's its own block. And you could make like 3 or 4 of them, and they're not going to be stored in the same place. And you could have different values for all of them and all that stuff. If you have a static property, like 0 here, for example, right, then what you're saying when you use the static keyword is, okay, I only ever want there to be one 0 property stored somewhere, right? And so Swift will look at that and say, okay, cool. So we're going to make some memory over here that all vector3s know how to access. All of your struct type know how to access, right? And that's just going to be just a piece of global shared state, right? And so, because it's a constant, a let constant, it won't ever change from what it gets assigned to initially, right? So you can do cool things like, here we have done static let 0 equals vector3 with zeros passed in. That means that moving forward, if we ever want to get a new 0 instance, then we can call vector3.0, and it will create a new 0 instance for us. Except when, It won't create a new one for us. It will access the existing one that was assigned to 0 already. And 0 exists for all vector 3s. It is the same 0 variable for all of them, right? And you can access it by, instead of having an instance, you can access .0 on an instance of vector 3. So if you created a constant that you assigned vector 3 into, you could call .0 on that instance. But you can also call it just from the type keyword. So, or from the type definition, keyword, yeah. So vector 3, right, our type, you just call vector 3.0, and that will get what you had. You can also set this up so that your static property does create a brand new vector 3 instance every time, right? And then it's more like a function that has a return type, and you do that with a get computed property. Or with a function, a static function, another way to do it. Yeah?
So in the future, if I create like 3 different vector 3s, all of them will have access to the same 0 that is stored at a special place?
Yes, yes. In this case, yes. Because we're doing an assignment, right? So because we're doing this assignment here, basically, and because it's static, it's like, oh, this will only ever happen one time, right? And then we just have access to it in the future, right? If it was a computed property where we had a getter inside, right, and no setter, right, just a get, and then we did this vector 3, like, and that's what we return from the get, that's essentially the same as having a function that gets called with a return of vector 3 and then creates a new vector 3 instance within it whenever it gets called, right, and then it gets returned. If that is confusing, I can open up the playground and show the variants that I'm talking about. But
what you just said was, so the function will get stored in this special static place,
Mhm.
but what it returns will always be a new.
right,
Okay.
yeah, and because functions and computed properties and stuff, like, they don't get stored in the same way as variables and values, like constants and variables do, right? Variables and constants are data, right? Functions and computed properties are code, right? So a static function is stored kind of in the same way as a regular function. Whenever you create a new instance of a type, you are not copying the function code into memory as well. It has a reference to where all of the methods for that type are defined, and then it knows how to kind of tie them together, right?
So there's no point to have a static function then?
You could have a static function so that you don't need to call an instance on it. So like if you don't want to have a vector 3 instance to call a function, right? Then you could create a static function for that reason. The other thing to note is with static functions, you cannot access any non-static stored properties or computed properties, right? Because then it's like, well, I'm static. I don't know which instance you want me to pull this stored property from. I don't have a static property that you're trying to access, right? It's almost like creating like 2 different types, sort of, within the same type. So, cool. Okay. Any other questions about statics? Alrighty. 10-minute break. So there we go. Off to the races. Have fun. Enjoy.